All right, in this video, we're going to focus on carrying forward on wave characteristics. In the last video, we described the wave equation and what waves look like and definitions of waves. And now we're going to look at some more characteristics where how do we draw waves on paper. So something that you're going to come across in the text is when we describe wave fronts or rays. That's how we draw the propagation of wave in a medium. And we're going to start by looking at some characteristics of intensity. Okay, how do we describe the energy or intensity of a wave that is hitting you, and how does that relate to the amplitude of the wave? Okay, so these two pictures that we have in front of us is general pictures that you'd see in every textbook of waves being made in water by a disturbance, okay, such as a little boat bouncing up and down, or if you throw a rock into a pond, it'll generate these concentric rings, okay, and those rings are waves that will be propagating across the pond. Often you'll see those rings tend to kind of die out. They don't actually make it all the way to the end. They'll die out in terms of their intensity. Here, if I keep pushing my finger in and out of the water, I can create a general wave pattern. In order to keep those waves a fixed distance apart, my finger has to be going up and down with a fixed frequency. All right, and these crests that you're seeing are called wave fronts. You can see the crest. It's much easier to see the crest than it would be the trough of a wave. And what we can see is that those waves propagate out spherically on the surface, okay, and they get larger and larger and larger. And what you're going to see in this video is that that energy is going to spread out as the wave goes along. All right. So what you will see in textbooks or in questions on paper, it's hard to draw a wave in 3 dimensions. So we often draw the waves in the form that you see over here. Okay. So this picture is of a wave pattern from above. Imagine you're in a helicopter looking down at the water. The dark lines over here would be the crests of a wave, or what we call the wave front. The wave front, or the crest of the wave, is the part that you would see above the water. And this white part would be the troughs. Okay, and this is the side view of what you're seeing over here. These are the crests or the wave fronts. Okay, so the wavelength would be the distance between 2 consecutive wave fronts. Okay, that would be my wavelength. All right, and then if you look again from another side view, this is just another contour image where these are successive wave fronts. And the distance between each, let's change the color here. The distance between each wavefront would be my wavelength. All right. Now, perpendicular to the motion of those wavefronts would be this arrow that you see over here. And that arrow is called a ray. Okay, so we can draw the direction that the energy is propagating. That would be my ray. It shows the direction that the energy is propagating. And these wave fronts show the direction that the wave is moving in a medium. All right, so we can depict waves in terms of rays or wave fronts, and you'll see when we're going to use either or in problems later on. All right, so let's get to it. How do we describe the amplitude and intensity of a wave change as it moves away from the source? So remember, I had these pictures of these waves moving from the source, and you can see in this diagram, it depicts it a lot better, where the intensity seems to drop off as the wave is moving through the pond. It tends to weaken out, okay? And that's because the energy of the wave is going to be distributed through the medium a little bit. All right, so the energy of a wave, as you've picked out in the simple harmonic motion, energy is directly proportional to the amplitude squared, okay? So if I look at the amplitude of a wave, this one that I see here, that's my amplitude. If you square that amplitude, that is proportional to the energy. And we know that in the ocean. If you step into the ocean and a wave comes that's double the size, the energy is going to be 4 times, okay? So 2 squared. If I doubled the amplitude of a wave, the energy is going to be 4 times the original energy. And we've all experienced that, where you get blindsided by a wave. You got to understand that it's a squared function. So just a small difference in amplitude carries a squared function in energy. Okay, so energy is proportional to the square of the amplitude. And so would intensity. So the intensity of wave, which is what we're going to learn about, is also proportional to the square of the amplitude. Okay, so what do we mean when we talk about the intensity of wave? Whoa, that wave was really intense. It pushed you over. Okay, well, the intensity is a measure of the energy per square meter, or more commonly what we see, they wouldn't say joules per meter squared. More commonly, it's the energy that passes you in a second per meter squared, which would be watts, the power of the wave per meter squared. And that's what you see over here. Okay, so this is the more typical way of describing intensity. It's the watts, the joules that pass you per second per meter squared. Okay, now how does the intensity of wave change the further away we get from it? Well, the intensity follows something called the inverse square law, which we have over here. And it'll make sense once you see this diagram. Okay, so here's a light bulb that's emitting electromagnetic waves with an energy at the source. Let's say that's going to be the point where you're going to get the most energy you can. And then those waves are emitted spherically, not just in 2 dimensions, but in 3 dimensions, so like a sphere. Okay, they're emitted over and over. Okay, so that energy is going to be distributed over the entire surface area of a sphere. So you can imagine it's going to get diluted. And this diagram is very common. You can imagine that if I took the intensity of light that hits that area, okay, how many watts of power per meter squared, and then I moved over here, if I doubled that distance, okay, now that amount of energy is only going to account here, 1/4. Okay, so it's going to be diluted by 4. And then it'll be diluted, if I went 3 meters, by 9. Okay, so the intensity of light is proportional to 1 over r squared. That's what the inverse square law relationship means. Okay, so as I double my distance, the intensity is going to go down by 1 over r squared. Okay, so it gets significantly reduced. All right, so the actual formula for intensity is right here. Okay, so intensity, this is when I look at it in terms of energy, but let's take a look in terms of watts per meter squared. The intensity is equal to whatever your source energy or source power is, so whatever that source energy or source power is, divided by 4 pi r squared. Now where 4 pi r squared comes from, that is the surface area of a sphere. Okay, and so what's happening is that energy is being spread out over the surface area of an entire sphere. Okay, so the larger the distance, the larger the sphere, the larger that energy is going to get spread out. So the intensity is going to be that source of energy divided by 4 pi r squared. Okay, you'll find out there's another value in here that we'll talk about later on, but to simplify things, the intensity is equal to the energy divided by 4 pi r squared, or the power of the original light bulb divided by 4 pi r squared. So what I want to do is I want to go through a few problems and see how we can apply that. Okay, so the first problem here says calculate the intensity of light emitted by a 100-watt light bulb at a distance of 2 meters away from the source. Okay, so the equation is I is equal to power divided by 4 pi r squared, which is going to be equal to 100 watts divided by 4 pi 2 meters squared. Okay, now if you put that into your calculator, you'll get 1.99 watts per meter squared. So what does that mean? So if this is my light bulb, okay, in the corner of my room, and it's a 100-watt light bulb, if I put a light sensor just 2 meters away, okay, that's probably, how far you're sitting away from a light that's in the corner of your room. If you put a sensor at that place, instead of it being 100 watts like the light bulb is, you're going to be down to 2 watts per meter squared, okay, which is significantly less intense. Okay, so you'll notice that the closer you get, the brighter that light bulb is going to get. That totally makes sense. All right, so this would mean 2 watts per meter squared means 2 joules of energy is passing that point per second per meter squared. Okay, and we'll need to use that value later on. Calculate the power of a light bulb if the measured light intensity is 10 watts per meter squared at a distance of 1 meter from the source. So if I have my light bulb, okay, and I am 1 meter away, and the light intensity is 10 watts, they want to know how many watts that light bulb is. The same formula, intensity is equal to power divided by 4 pi r squared. So the intensity at that point is 10 watts, which is equal to power divided by 4 pi 1 meter squared. So then if I take 10 watts and I multiply it by the denominator over there, that should get me the power. So 10 watts times 4 pi times 1 meter squared gives me a power of 125.6 watts, okay? Next question. Create a linearized relationship between the measured intensity and the distance from the source of a wave. So if we were going to do an experiment, if I was going to design a lab like two of the students did this year in grade 12, they designed labs with intensity of a flame or intensity of a light. Okay, for example, Bryce looked at how does a change in the intensity of a light. So if this is my light bulb, how does the intensity of light change as a result of the voltage that we plug the light into? Okay, that was his IA. So he did an experiment to look at the intensity at different places, and he needed to create a linearized relationship so that he can work back and figure out the power of that bulb. So the formula, intensity is equal to power divided by 4 pi r squared. If I wanted to make a linearized relationship between measured intensity and distance, how would I create a straight line relationship? We've been doing this all year. If I'm measuring my intensity, that's going to be on my y-axis. If I am changing the distance, that's going to be 1 over r squared. And if I graph that, that should be a straight line. And the slope of that line would be power divided by 4 pi. Okay, so if he would measure the slope of that line, he can then calculate the power, all right, by then taking the slope and multiplying it by 4 pi. Okay, that's all I got for you guys in this video.